In this video, we'll see how we can construct a form of object-oriented programming into Scheme. So in Lisp and Scheme literature, the word object often refers to just a piece of data in memory, but here we're now talking about objects in the object-oriented sense of the term. So in the object-oriented paradigm, we create a bunch of interacting partitions of state of the entire system, which are called objects. Now, the design of solutions in this paradigm is more closely related to human concepts, which can reduce human effort and support the design of systems that are far more sustainable. The modularity in specific of the objects allows for simplified refactoring and debugging and division of labor and even extension into our designs. So object-oriented design is a very important design paradigm, even in this Lisp course. So in the object-oriented design, we need to decompose a system into a model of interacting objects, where each object represents its own environment. So these objects can contain complex data, but that data is localized to each self-contained object. And then it's combined with methods or behaviors that interact with that data. That is to say, functions or methods which close over the same environment as that object's state. And then all of this abstracts the object's inner complexity down to just a simple interface of functions. So all told, if we want to implement an object-oriented paradigm in Scheme, we need three things. We need a persistent local state per object, so a state that's private to the object itself, but persistent. We need behaviors or methods that have access to that hidden local state and can mutate it. And we need a public interface that allows code outside of this object to utilize those behaviors without exposing that private state. So let's go through these in turn. So starting with, we want to create persistent private state, and we'll do this using closures. So functions have private local variables already, right? If I define x to be 0 inside a function, then that x is going to be local to that function. It's not going to be accessible outside of that function. But the problem is the extent of those local variables only lasts as long as the function exists. Once the function's done, the local variables get garbage collected along with the rest of the activation record. So what we need to do is create a way of having essentially those local variables or those scopes persist after the function has already exited. So recall, a closure is a function that's bundled together with its enclosing environment pointer. So the environment that's enclosing the closure, let's say the parent environment, will persist so long as that referencing environment does, so long as that closure exists. Now, free variables from that outer function can still be accessed by that inner function throughout the entire lifetime of that inner function, even if that inner function has been returned from that outer function and that outer function has terminated. If that inner function still exists back in global scope or wherever it's been moved to, if its body is executed, it still has access to the free variables in the environment in which it was declared, which is to say those free variables will persist. So consider the code here up on the slides, and actually let's take this over to where I can draw contours into my PowerPoint. So we have an example piece of code here that's just used to demonstrate this idea of persistent state via closures. So we have this global variable z, we have a function x that creates a lambda, and then we'll use that function to create two closures, and then we'll access those closures to see how they interact with their free variables. So let's walk through this line by line. So on line 1, we define a variable z to have the value 2, so we get a binding in the global scope from z to 2. Now we're on line 2. On line 2, it says define this function called fun. So we have a name fun bound to the lambda on line 2, and that was declared in the global scope, so we have a reference pointer to that. Now we're on line 4, which comes after fun. So the next thing is 5 here, which says define closure 1 as the result of running fun on the value 3. So if I call fun 3, 3 goes into x throughout the body of this function, but you can see the body of this function is just a lambda. So if we call fun 3, we create a contour for fun prime, where the parameter x is bound to the argument 3, and then we're on the line 3 here to execute the body of that function. But again, as we look at the body of this function, the entire thing is just a lambda. So if we execute the body of this function, it doesn't execute any of these steps. It just creates a function that takes in one parameter and will eventually execute these steps of its body. But for now, it's just a function object. Now, that function object isn't actually bound to anything, so it doesn't appear in our contour here. But if it were, if I had said, for example, define f to be this lambda and then return f instead of just returning the lambda itself, we'd have a binding for f to the lambda on line 3 declared in the local scope. Okay? But now the issue is we're not doing that, and we're just immediately returning it. So we're still creating that closure, it just doesn't show up in our drawing. So the closure is still between the lambda on line 3 with a reference pointer to this fun prime. But instead of binding it inside fun, which is disappearing, we're just going to return that lambda and bind it to closure 1 instead. So this might look a little bit odd, but the next step says we return the thing that lambda produces, that closure object, and we're going to call that closure 1. So the thing that came out of fun prime is the lambda defined on line 3 that was declared inside this scope. Okay, so again, when you create the closure, it always creates the current scope as the parent scope, but again, those functions can move around, so as they move around, their pointers don't change, so the arrows start to look a bit strange. So in this case, this was declared on line 3 inside this function. Now, because there is something referencing this contour, we can't destroy the contour. We still need access to it later on. So up until now, when a function's done, its closure disappears. This essentially represents the garbage collector that will eventually come through and see that nothing is using this activation record, so it can be garbage collected. The way a garbage collector essentially works is it goes through all the bindings in the global environment and follows all the references to all these other sections of code, and if it can get to a piece of code to one of these activation records, then that's still a potentially active piece of code, or a potentially active block of memory. In this case, because we have a pointer pointing to this contour, to this scope, that is exactly what happens. We have a way of getting to this contour, so it's still potentially relevant. If we didn't have that, then fun prime could get garbage collected, as we've seen in our previous contour models. Okay, so that's the end of line 3. So notice in this contour, there's no more line numbers anymore. It's not being executed anymore. These represent active executions or deferred executions as well. But there's nothing else running inside the body of fun. The body of fun is done. It's only being used now because it's being referenced. So it's only really being used for its variables. All right, so we're on line 6. So line 5 said define closure 1, and now we have closure 1. So line 6 says do the same thing with fun, but now with the argument 4. So we create a new contour for fun double prime with x bound to the value 4. Now we're on line 3, and line 3 says execute this lambda, or so execute and return the object that comes out of this lambda. So again, we get a new function that's the lambda on line 3, but it's declared in this current scope. Since we're currently in fun double prime, that's where the referencing pointer would point to. But again, we don't bind it in this scope. We immediately return it and bind it to the name closure2 in the global scope. So this collapses, or returns rather, and we end up back in the global scope. We bind closure2 to the lambda on line 3 that was declared in this scope, where x has the value 4. All right, so we're on line 7. So the next thing that happens is line 8 here, where we say define R1 to be what happens when we call closure 1 on the value 5. So again, closure 1 and 2, these are just functions. These represent this lambda here. The lambda on line 3. So if I call closure 1, the value 5, closure 1, if we're in the global scope here, we're on line 7 in the global scope, closure 1 is the lambda on line 3, and it takes in this case, the value 5 for the parameter y, and then we walk through the body of that function, times x, y, z. So when we're running a procedure, we need to create a new contour for that procedure. If we're doing closure 1 here, then where we create that contour is we follow this arrow, and we create it inside the box for fun prime. So the scope for closure 1 is nested inside its parent scope, even though its parent scope has already essentially finished. Notice the return pointer doesn't make any stops in fun prime. It goes straight from closure 1 to where closure 1 was actually called in the global scope, but it still runs in the context of its parent environment. Okay, so closure 1 gets the value 5, so y has the value 5. We're now running this, the body of this lambda, the times x, y, z, within this current contour. So if I'm where my mouse is, and I say, what's the value of y? Well, that's easy because it's this local y, it's bound to 5. If I need the value for x, well, I don't find that, so I go looking into the enclosing scope, and there it is with the value 3. If I go looking for Z, I don't find it locally. Go to the enclosing scope, it's not there. Go to the next enclosing scope, and there it is, Z is bound to 2. So we have times x, y, z. Also should have done a lookup for the asterisk, which would brought us to the primitive environment for the multiplication function. All right, so now we have multiply, 3, 2, and 5. And that gives us, 10 times 3 is 30. So all of that math occurs in here, and then the value is the value of this whole lambda, so that gets returned back to line 8, where it gets bound to the symbol R1. So we click, and we get R1 has the value 30. So notice when that closure appeared, it appeared in here. Nothing's referencing it anymore, so that closure can now disappear, or sorry, that contour can now disappear. Okay, so that was the end of line 8. So now we're on line 9, where the similar sort of thing happens, but now with closure 2. So if we're running closure 2, that's the lambda on line 3 that was declared in this scope. So if we want to create a contour for that, we create that contour inside this parent scope. So we go back to where it was created and access that. It's kind of like if you're moving out of home, you can always go back home and still raid the fridge of your parents, right? You can still grab their free variables and access them when you need to, even after you've left. So with closure 2, we get the value 5, so y is bound to 5. We get times x, y, z. Y is local. X is found in the enclosing scope and now has the value 4. And z is still the global variable, has the value 2. So we got 5 times 2 times 4 gives us 40. So all of that gets computed inside this scope here, returned to line 9, and bound to R2. Now notice the key difference here. So we ran closure 1 and closure 2 are both this lambda on line 3, right? They're the same lambda. Essentially they did the same math, right? When we ran closure 1, we gave it the value 5. The only key difference is the environment in which they were created. Closure 1 was created in an environment where x was bound to 3. Closure 2 was created in an environment where x was bound to 4. And because of that, when we ran those two closures, even with the same values, the values of their free variables were different because they exist in different environments, so we got different results, specifically 30 and 40. All right, so we created persistent state. Notice the state of these values, x is 3 and x is 4. Those persisted over time. They're essentially private, right? If we're out in the global scope, we can't refer to x outside of fun, but the closure here still has access to that variable x even when it's run from the global scope. So we have essentially created these local variables that are private to anything that was created inside that function, but inaccessible from anything outside of that function. All right, I think that's it for that example. Good. So on to the next one then. So we can create private variables that persist after functions exit. So now we need a way of modifying that private state. So we've already seen a way of modifying state. We've seen the assignment operator, or set. This is used to change the values of existing bindings. So if we already create one binding, then we can set the value of that binding to be a different value throughout time. So consider, first off, a simplified bank account. So we have a bank account here that's only capable of doing withdrawals, and we have this global variable balance that represents our total bank account amount. And then withdrawal is just able to remove values or remove some amount from that total balance. Right, so to be time varying, we use set inside our withdrawal. This mutates this global variable balance to be changed through time. And we'll see that we have 3 commands that are identical, so 3 calls to the same function with the same arguments that will yield 3 different results because we have time varying state. So let's walk through this one. So line 1 says define balance, so we get balance set to 100. Line 2 says define the function, so we get the function withdrawal as the lambda on line 2 declared in the global scope. It's not as important to this example. Right, and then next is line 7. So on line 7 we execute this function. So we call withdraw with the value 40 bound to amount. So we create a new contour for withdraw single prime, where amount is bound to the value 40. And we're on line 3 here, the body of withdraw. So that says if balance is greater than amount, greater than or equal to, which it is in this case, 100 is greater than or equal to 40. So we begin, we go to line 4 here, and that says set the balance to balance minus amount. So the next step here is balance gets changed. So notice if we're in this scope, in the scope of withdraw prime, and we say what is the value of balance, well we don't find it locally, so we go looking into the enclosing scope, and that's the one we change. So when we say set balance, we're setting the enclosing scope variable. Right, and then that says return balance, which is the current value balance, which is now 60. So if we return that, we get the value 60. And then line 8. So line 8 essentially does the exact same thing. It says withdraw 40. So again, 40 goes into amount. We get a new contour, withdraw double prime, where amount has the exact same value. We're still on line 3, and we ask, is balance greater than amount? Well, the comparison is different because balance has now changed, but amount is still less than balance, so we can still withdraw some money. So in this case, we set balance to balance minus amount again. 60 minus 40, that gives us 20. And that's the end of withdraw, so that contour disappears as well, and we move on to line 9. Then on line 9, the same sort of thing. Again, we create a contour for withdraw with the amount bound to the value 40. But now when we say, is balance greater than amount? Well, 20 is not greater than 40, so that's false, and we get insufficient funds as the result. So with normal functional programming, or pure functional programming, if you will, the notion of referential transparency means that these variables don't change over time. So if we have 3 function calls with the exact same arguments, we should expect the exact same result. But since we have mutable data, the ability to assign values to existing bindings, we no longer have that. We now have versions of variables through time. So now we have time-varying state with this set operation. Now, the problem here is, it works. We have a means of modifying state, but the problem is that state is not private state. We want to have these, if this is to be used in the construction of objects, we want to have it so that that state isn't accessible from outside of the object itself, right? If I was creating a bank account and balance was set to public, that would be a problem. We don't want everybody being able to just mutate this. We want the bank account to control its own balance, and we'll eventually create an interface for interacting with that private variable later. Okay, so first off, we need to make this state private, and we've kind of already seen how to do that. We can do so using a closure. So we can create hidden time-varying local states. We already have the time-varying state. We've already seen sort of persistent local state. Now we need to create all of those together, hidden time-varying local state. So let's go on to the next example here. So we're going to do a similar sort of thing. So most of this is the same. So all of this code is going to do the same stuff in terms of withdrawing some amount of money from an existing balance. But the difference here is we're going to create a closure to make this balance private within this make-withdraw function, but persistent outside of the actual withdraw behaviors. So what we're going to do is make withdraw. We're going to create a withdraw quote-unquote object, a withdraw closure that exists in the scope of a function's environment that has this balance already bound. So it's one step below global, so you can't actually access this balance just as a variable, but this closure will still have access to it. So let's walk through this one. On line 1, we define this make withdraw function. So we have a function bound to the lambda on line 1 declared in the global scope. And then all of this is inside that function, so we jump down to line 8. So line 8 says call make withdraw with the value of 100 for balance. So create a new contour for make withdraw. We'll eventually call what comes out of that W1, but we have to get that value first. So a new contour for make withdraw, the parameter balance bound to the value 100, and now we're on line 2. So line 2 and lines 3 through 6 as well are all part of one big lambda. So line 2 says create that lambda, and lines 3 through 6 are the body of that lambda. So if we create a lambda here, it has one parameter, and here's the steps, and then that's the entire body of make withdraw. So this function call essentially just returns that function or that closure. Again, if we were to have bound it to a value and bound it to a name and return that name instead, we would have the lambda on line 2 declared locally here. But again, we're not doing that. We're immediately returning that lambda, and we're going to bind it to a name out in the global scope instead. So we're going to say define W1 as the thing that gets created by this lambda. So it's the lambda on line 2 declared in make withdraw. So on the next picture, we end up with make withdraw returns that lambda. That's the lambda on line 2 declared inside make withdraw single prime. Okay, so we've created a closure here. We have this function that's declared inside this other function. We have this persistent variable. Again, notice there's no execution pointer in make withdraw anymore because that function's done. It's essentially done what it needed to do. It created this withdraw behavior. But it also has this persistent variable balance that's hidden out of the global scope but still persistent. Okay, and we're going to do the same thing for W2 just to show that there's independent existences between these quote-unquote objects. So we call make withdraw again with the value 100, so we get make withdraw double prime, a new instance of this variable balance, because it's in a new scope, happens to have the same value. Okay, so that's on line 2. Line 2 says construct and return that lambda, and we'll bind that to W2. So just like we did before, we get a binding for W2 as the lambda on line 2, this guy here, that was created inside make withdraw double prime, so this scope in specific. All right, so then the next few lines are just doing withdrawals. So withdraw $50 from the first account, withdraw $70 from the second account, withdraw another $40 from the second account, and withdraw $40 from the first account. So let's go through those one by one. Line 10 says withdraw $50 from that first account. So call W1 with the value 50. So because we're assuming lexical scoping says when we create a contour for this W1 function, we're creating it at the end of this pointer here. So inside its parent environment. So W1 gets a scope inside here. So we get W1 prime, the amount value, 50, gets put into this variable, and then we just run through the body. So we're on line 3 that says, if balance is greater than amount. Well, there's no variable called balance, so we go looking into the enclosing scope, and there's a balance. That's set to 100. 100 is greater than 50, so that's true, and we can walk through lines 4 and 5. So on line 4 it says, set the balance to balance times amount. Again, all the balance references refer to the free variable balance here, and amount refers to the local variable amount. So 100 minus 50 is 50, and that's what happens on line 4. We mutate that variable, this enclosing scope here, and that's it. So we return the value of balance. This would return 50 back to line 10. Okay. Then on line 11, we call W2 with 70, and a similar sort of thing happens. We follow this reference pointer to see where to create that contour. It's in the other make withdraw contour, so we create W2 prime, and off it goes. So the amount is 70 because we passed in a 70. 100 is greater than 70, so we walk through, we set the balance to balance minus amount, so we change this instance of balance. Notice a separate instance because we're in a separate scope. And that gets 100 minus 70, so that becomes 30. And then this returns the current value of balance, and it's done. So this returned 50, this returned 30. This one here, now we're still with W2, we pass in the value 40. So we go to 40 here. Again, we create another scope. That should be a double prime, that's a typo. So W2 double prime gets the amount 40. Walk through all of this. Is balance greater than amount? It's not, so we get insufficient funds. And that's what that returns, is the string insufficient funds. Okay, and then for W1, we run that again. So W1 gets created in this left scope again. Again, that should be double prime, call that a typo. So amount is 40 as well, but it's within a scope where balance is greater than 40. So this is still a valid operation, and in this case we get 50 minus 40 is 10, and this would return the value 10. So even though W1 and W2 are created similarly, they have independent existences because each one of these calls to make withdraw returns an independent lambda that's created in a separate scope, right? Each call to make withdraw creates a new instance of this make withdraw activation record or contour. And each one of those produces its own lambda, which is unique to the specific contour in which it was created. Or more specifically, it's tied to that contour. So even though it's running through the same set of arguments, when it refers to a free variable balance, it refers to the enclosing scopes balance, which have independent existences because of the independent scopes. All right, so now we have hidden state, right? We've hidden that balance inside these functions. We have mutable state because we're able to change it through time. We have different values coming up with the same function, so time varying state, and it's local. So we have time varying local state, which is pretty much most of what we need. The next is we need to have some sort of interface. So in order to create an interface here, we want to have the ability to provide functions to the user. So for example, we want to create a bank account. We want to be able to provide deposit and withdraw behaviors, but we don't want the user of those functions to also have access to this variable balance. So this ends up working pretty well because we already have this hidden state. So the real trick is how do we make an interface of functions available to the user of our objects. And the way we'll do that is by using what's known as a dispatch or a message passing style. So message passing style is essentially we have a function inside our object that listens for symbols or strings as messages and will return the appropriate function. So we have control over which functions it can respond to. So if somebody asks for a withdraw or a deposit function, we can provide those functions to the caller. But if they ask for, let's say, a change password function, that's not an ability that we can do with our bank accounts, then we won't have that. We won't be able to provide that to the user. So we're controlling the allowable behaviors while still keeping all of the private state private. Okay. So the way this works, let's actually just see the code for this. So it's pretty similar to the previous example. We're going to create a closure around this private state. So we're going to create a closure around this balance variable. I've used a let instead of passing it in just so that I can give it a default value. But as we've seen in previous examples, since this let is pretty much the entire body of this function, looks like I missed a bracket again. Oh no, let and then define. Okay. Since this let is this entire function, you can pretty much consider it as part of the make account, just with a default value for the symbol there. So we've created a closure in which there's this private variable balance, and we've constructed a number of functions, in this case just withdraw and deposit, and then a dispatch function that acts as the message interaction or the interface for anybody using this object. So dispatch takes in a message. In this case, we'll assume it will be symbols. So if they pass in the deposit symbol or the withdraw symbol, then we'll give them back the deposit function or the withdraw function. Notice these are just the symbols associated with withdraw and deposit in the local environment. So we'll return those objects, and that's what can be used down here. I think this will make more sense once we walk through the contour, so let's go through line by line here. So line 1, we say define make account, which just creates a binding between the symbol make account and the lambda on line 1. That's declared in the global scope, so that pointer there. And then everything else is inside that function, so we jump down here to line 17. On line 17, it says run that function and label whatever comes out of it as account. So when we run this function, we create a contour. So we get a contour for make account. It doesn't have any parameters of its own, but again, its entire body is a let, so I've done the double contour style here rather than having a nested let inside, where the balance is bound to the value 0 as the let dictates. Now, inside the body of this function and let, we say define withdraw, define deposit, and define dispatch. So for on line 3, we define withdraw. That gets bound into this local scope, so we get withdraw is the lambda on line 3 declared in this local scope. Similarly with deposit on line 8, we get deposit is the lambda on line 8 declared locally. And similarly, line 11 does something called dispatch. So we get dispatch is the lambda on line 11 declared locally. Okay, that's all of those. And then the only thing this function actually does is returns dispatch. So the value associated with the name dispatch is the lambda on line 11. Okay, so that's what's getting returned. The lambda on line 11 along with this pointer. Again, think of this as a closure or an egg around 2 pointers. That's the thing that's going to get passed around when I say return the dispatch function. So that gets returned to line 17. And on line 17, we say define account to be whatever got returned. So in the global scope, we get something called account, which is the lambda on line 11 pointing to where this one pointed to, which is to say this contour. Okay, the make account contour. All right, so that makes one account object. And then to use the account object, what we need to do is pass information into the dispatch function. So if we want to access the dispatch function, well, as it turns out, the thing that we've been calling this account object is just a dispatch function, right? That's the lambda on line 11, which is this function here. So if I if I provide an argument to this function, it's going to call dispatch and use that as the message parameter. So if I say account deposit, deposit goes into message, and we walk through all of this. So we create a new contour for dispatch. Now, because dispatch was declared with a reference pointer to this make account prime contour, that's where its contour will be created. So we get account in here. Now, account has been given two names, right? This lambda on line 11 is a singular thing. We copied it from here to there and gave it a different name. So technically you could call it one of two things. If it's clearer to you to call this dispatch because it's currently doing the dispatching part of the whole account object, that's fine. On the other hand, it was called using the term account, so if you want to call it that as well, that's fine. Just pick one or the other. Don't use both because it's a bit confusing, but be consistent. If you use it dispatch, then the next time dispatch occurs, it should be dispatch double prime, and then dispatch triple prime. If you use account, then it should be account single prime, account double prime, etc. Okay. So we return dispatch, that got named account. We have the lambda on line 11, and that's now what we execute here. We say account, taking in this deposit symbol, so just the word deposit essentially as a symbol. That goes into message, and then we ask, what is the value of this message? Is it equal to deposit? If so, then return the deposit function. So if we're in here and I say, what's the value of message? Well, we can see the local variable here has the symbol deposit. So EQ deposit deposit, yes. All symbols that look alike are the same, so that's fine. So then that's true, so we return this deposit. Now we're not going to return the symbol. It says return the thing associated with that, right? That's like if we just used the variable x, we're going to return the number associated with that variable. In this case, we have a variable associated with a function. So if we look locally, we don't find that symbol anywhere. So we go into the enclosing scope, and sure enough, there's something called deposit in this table. That's the lambda on line 8. So the thing that's going to get returned is the lambda on line 8 declared in this local scope. Okay, so this call here, account deposit, will turn into the lambda on line 8. So in the next step, which says apply something to 100, what we're applying is the lambda on line 8 to 100, or in other words, the deposit function to 100. Okay, but specifically the deposit function that was declared in this scope, as opposed to if we had made a separate make account. Okay, so we call deposit, we get back the lambda on line 8, so that's here now. It doesn't really show up in our model because, again, we don't bind the result of this to a name. We just immediately use it. So we now use that on the value 100, and we get a similar thing. So if the lambda on line 8 declared here was returned, then we run that function. We're still running it where it was declared. And now we're depositing 100. So amount equals 100, and we walk through the body of the lambda starting with line 9. So line 9 says set balance to balance plus amount. So balance was currently 0, amount is 100, so we change that. Okay, and then line 10 says return the current value of balance. So again, there's no local balance in deposit, so it's all referring to this object's local state, if you want to call it that, or an attribute value. So when we return balance, we're returning this free variable balance, or specifically the value 100. So all of this ends up equaling the number 100. Okay, so that returns and is done, and we move on to line 19. Line 19 does a similar sort of thing. It says call account with the value withdraw. Now again, this account refers to the dispatch function, so what happens first is we get a dispatch, and then we have withdraw. Oh, I did it again. So this also should be a double prime, not a single prime. Call that a typo. All right, so account withdraw with the value 60. We haven't gotten to that part yet. So account withdraw takes in the symbol withdraw, walks through all of this because it's still just the lambda on line 11. Does it equal the symbol deposit? It doesn't. It equals the symbol withdraw, so we'll return the thing associated with the name withdraw. Withdraw is associated with the lambda on line 3, so we'll return that lambda back to here. Or back from here, I should say, back to line 19. On line 19, we had the lambda on line 3 applied to the value 60, so this returns, and then we run that function withdraw with the value 60. Okay, and walking through the body of withdraw starts on line 4. If balance is greater than amount, it is, then set the balance to balance minus amount, just like we did with the previous examples. So we shrink the value of balance, and then we return the current value of balance back to line 19. Okay, and then we go on to the next one. We call withdraw with the exact same amount, and we get, first off, the dispatch function, which returns the withdraw function. We apply that withdraw function to the value 60, so that runs again. And now, even though it's the exact same function call, because we have this mutable state that's changing through time and persisting between function calls, even though we have the same inputs, we get a different output. In this case, insufficient funds. All right, and then that returns, and the whole thing is done. And that's that. So we can see we made objects within a sort of functional language. It's not a pure functional language because we do have the assignment operator, but that was the only addition we needed, and we can construct objects out of this message passing style with everything else that we know. That's pretty much it. So this is it's an example implementation of the general object-oriented concept. There's other ways of implementing object-oriented programming, obviously, but this is one way to do it. And throughout the rest of this course, if I ask you to construct an object, this is the structure I mean. I want you to create this closure function, so an outer function that constructs a bunch of inner helper functions, as well as a dispatch function, and returns that dispatch function. It doesn't need to be called dispatch, but it's a function that essentially performs the message passing behaviors. So we can pass in a message and get back just those functions that are available. If we passed in something that didn't exist, we get an unknown command as a response instead of having all the ability to run that function on other states. All right. So that is it for this video. It's also it for this chapter. So in this chapter, we took pure functional programming and turned it on its head by adding in the assignment operator. We have mutable state instead of our previously referentially transparent language. We now have the ability to construct bindings and then change those bindings over time. Because of that, we can no longer use the substitution model. So if you have any code going forward from now that involves set or set car or one of these other assignment type operators, you can't use the substitution model to represent the process, or at least not accurately. So to that end, we constructed the contour diagram, or we explored the contour diagram for representing environments, that is to say the bindings of variables and the nesting of scopes. And that's it for this video. In the next video, we will talk about the Metacircular Interpreter, which is essentially constructing a scheme interpreter inside the scheme language. And I'll see you in that video.